Okay, torque. So the symbol for torque is a Greek T. We can't use a capital T because we use that for period. We can't use a small t because we use that for time. So we use the Greek T, which is like a fancy script T, and it's called tau. For those of you that had me in grade 11, if you remember, I told you that if you stick with me, you'd learn the whole Greek alphabet by the time you were finished the 3 courses. So we're getting there. So this is torque. It's tau, okay? Now, up until this point, whenever we were looking at objects, we were always assuming they were point objects. So when forces were acting on them, we assumed they were always acting through the same point. And that was okay up until now. And so when we look at this, we would say, okay, the sum of the forces here is 0 because there's 100 newtons going one way, 100 newtons going the other way. And if the sum of the forces is 0, then we would have said the object was in equilibrium. And that would mean that it was either at rest or moving at constant speed, right? Equilibrium means that there's no net force acting on it, okay? Technically, though, that's not really true, because what if the object wasn't a point object? What if the object had dimensions, like most of us do? And so if there was 100 newtons of force acting up here, going one way, and 100 newtons of force acting down here, going in the opposite direction, now they're no longer going to cancel out the way they did over here. Although the sum of the forces is still 0, you should be able to see that this object is going to move. Not only is it going to move, it's actually going to rotate. And if I were to pin it on a spot, then you could see that it would rotate around this spot. And this spot that it rotates around, we often call that the pivot point. So now we have to stop and rethink equilibrium, because the sum of the forces is still 0, but the object is clearly not in equilibrium the way this one is, because the object is spinning. So now we need to say, well, actually there's 2 types of equilibrium. This type over here, when the sum of the forces is 0, this type is called translational equilibrium. And translational equilibrium is very simply sum of the forces is 0. Okay, now you would have heard of translational motion in math. In math, you would have translated functions. You would have moved them one side to the other. So translational motion is when an object is here and then it moves over here somewhere. And, okay, so that's called translational motion. And so when the sum of the forces is 0, there's no translational motion. Here, the object isn't moving from one spot here over to another spot. Here there's no translational motion. Some of the forces are still 0, but it's something else that's happening. What's happening here is called rotational motion. Okay? And so you can have rotational motion even if the sum of the forces is 0. This thing could be spinning. So in rotational motion, the sum of the forces can still be 0, but it's something else. It's the torque. Okay? And when you have spinning, then it means the sum of the torque is not 0. Okay? If the sum of the torque is 0, then we have something that's called rotational equilibrium. Okay? So sum of the forces is 0, gives us translational equilibrium. Sum of the torques equaling 0 gives us rotational equilibrium. If we have both, if we have the sum of the forces equal to 0 and the sum of the torques equal to 0, in other words, if we have both translational equilibrium and rotational equilibrium, then we get what is known as static equilibrium. Okay, so static equilibrium is when both the sum of the forces and the sum of the torques are 0. So not only is it not moving right left in a straight line, it's also not spinning. Okay? So now what the heck is torque? Well, if we go back and look at that object that has dimensions, with this force being applied here, then torque is something that has to do with the force you're applying and how far away from the pivot point when you apply it. This distance, how far you are from the pivot point, is also often called the lever arm. And for those of you that hang around people that use wrenches or screwdrivers, you'll often hear them say, oh, I need a bigger lever arm to get this bolt out because it's really tight. Or if you watch Big Bang Theory, Sheldon and them use a bigger lever arm when they're trying to loosen a nut on a flat tire because none of them have muscles. Geeks don't often have muscles. That's why I try not to make my muscles too obvious. Okay, so the lever arm, and the letter for lever arm is R. So what is torque? It's not a force. Please, when I ask you for a definition of torque, don't say it's a force applied over some distance that causes the object to rotate. No, torque is dependent on force, but it's not a force. The equation for torque is R, the lever arm, cross multiplied by F, the force being applied. It's the first time you're seeing two vectors multiplied in this way. And for those of you that have taken Science 12.2, you'll understand what this X is. For the rest of you, you're going to have to wait for Friday, because I'll use up the last 2.5 minutes of video that I have trying to explain it. For right now, you'll have to trust me when I say it's the same thing as saying torque is equal to R times F times the sine of the angle between them. The units for torque, well, the units for R is meters, and the units for F is newtons. And of course, there's no units on theta. So torque is measured in meter newtons. And we can't switch that order. That's not the same as a newton meter. A newton meter is a joule, but a meter newton isn't a joule. Because things that are measured in joules are scalars. Energy, work, they're scalars. But torque is a direction. The direction matters here. Okay? So that's all I'm going to do now. When we start class on Friday, I'll go back over this and then we'll keep going and it will make more sense. Or at least I hope it will. The only homework that I want you to do, I want you to read over the front page of the notes that I gave you, okay, for Friday. And the only homework that I actually want you to do is on page 4, I think it's 497, and it's numbers 29 and 30. I don't think I'm going to ask you to go further than that because I think that'll screw you up. But if you would read over, actually you could read over both sides of this page that says static equilibrium and torque. Okay, so it goes through the stuff that I just said in this video, and then it goes a little bit further, but not too much, and then that way on Friday when we talk about it, you'll be like, oh, this is easy. I can do this. Bring it on. Okay? Now go back and study for your test, finish up your assignment, and we'll see you bright and early, or at the beginning of class.